In a society heavily influenced by manufacturing, one of the main ways that robotics is used in the real world is in assembly lines and other factory settings where precision, accuracy, and speed are crucial. Pick-and-place robots observe and analyze workspaces, move to target positions, and manipulate items in various orientations. For the past 8 weeks, we used an open manipulator X arm, which features 4 revolute joints that give 4 degrees of freedom to replicate what an industrial robot would be able to accomplish, detecting and sorting balls into color-coded bins. While this may seem like a simple task that even a toddler can do, developing and implementing this into our robot arm was not easy.
The first step we took is calculating the forward kinematics of the robot. Forward kinematics is when you use joint angles to joint space to determine the position and orientation of the end effector to task space. Calculating the forward kinematics is often done according to the Denevit-Hartenberg convention, where frames of reference are selected for each joint along the kinematic chain, allowing us to get homogeneous transformation matrices from each joint to the next. By multiplying all these matrices together, we get a single transformation matrix that takes us from the base frame to the end effector frame. Substituting in a set of joint angles into this final matrix gives the position of the end effector with respect to the base frame, thereby solving the forward kinematics.
Now, what if we wanted to do the opposite? As the name suggests, inverse kinematics is the reverse operation of forward kinematics. Given the position and orientation of the end effector, inverse kinematics is used to calculate the required joint variables needed to get the robot there. When it comes to calculating the inverse kinematics of a robot, we were able to explore both analytical and numerical approaches. Analytically, we use the robot's geometry to draw the various robot links in different planes and use the law of cosines to solve for the angles. An important thing to note is that we have 4 degrees of freedom for this particular robot arm, but only need 3 to reach a target position. To prevent infinite solutions, we had to create an extra orientation parameter, which is the angle of the robot's end effector with respect to the horizontal plane. For robots with higher degrees of freedom, finding an analytical solution becomes extremely complicated. Instead, we can also use a numerical method to very closely approximate the solution. We used the damped least squares method, which takes an initial guess for joint values and iteratively adjusts them to reduce the error with the target position in task space, using a damping factor to improve convergence to the target. Numerical IK can also take other constraints into account, like end effector orientation or manipulability.
In order to create smooth, accurate movements, we use trajectory planning to define how position, velocity, and acceleration change over time. A cubic trajectory constrains position and velocity, while a quintic trajectory constrains position, velocity, and acceleration. These trajectories are defined by polynomial equations. By solving the equations describing each pose parameter, we can find the x, y, z, and gamma that the end effector needs to be at during any given time. Evaluating these equations multiple times a second and continuously changing the pose, which is targeted by our inverse kinematics, moves the arm in the desired path. By doing this, we can avoid sudden starts and stops, ensuring smooth movement and reducing excessive stress on our motors, while also preventing overshoot. Using this concept, we created additional trajectory planning methods. One takes in an arbitrary 3-dimensional parametric function and sends the robot along that path. This allows us to develop interesting trajectories like a helix curve. Another method sends the robot on a spline trajectory, allowing us to pick any number of points in space and smoothly travel through each one.
To be able to actually implement any of the previously mentioned strategies, we need to introduce a camera that we can use to analyze the color and location of the balls in our workspace. We use the simple USB webcam. With MATLAB's Camera Calibrator app, we are able to remove the camera's fish-eye lens distortion and translate the location of the pixels in the image to the coordinates on the physical checkerboard using the intrinsic and extrinsic camera parameters. These parameters are calculated each time the camera is calibrated to the checkerboard. If we know the location of a pixel in the frame of the checkerboard, we can introduce an extra transformation matrix, which will then allow us to map pixel locations to the base frame of the robot arm. To effectively extract color and position information of the balls, we need to send each camera snapshot through a processing pipeline. After the fisheye distortion is fixed, we apply a static mask to the workspace so we can ignore any objects outside of the checkerboard. We can apply different filters in the hue, saturation, and value color space to target the specific colors of interest. This results in a slightly noisy image, however, so we remove any pixel regions under a certain size. We then calculate the locations of each ball's centroid and associate it with its color for sorting. Finally, using simple trigonometry, we can eliminate the projection error due to the height of the ball. Combining these known centroids with the translation from image to robot frame, we can now find the task space coordinates of every single ball.
After putting all of this together, the forward and inverse kinematics, trajectory planning, and computer vision, our robot can scan for and detect different colored balls, go to its position, pick it up, and drop it off in a bin assigned to its color. We also added in a motion detector by comparing 2 consecutive snapshots, allowing us to do things like place balls on the checkerboard one at a time, and stopping the arm in between movements for safety. This was a great opportunity to implement the concept we've learned about robot control, as well as programming with MATLAB and using a GitHub workflow through Ubuntu to make the project organized and efficient.